Hello, welcome to the second lesson on energy, and today we are talking about gravitational potential energy, or we shorten it to GPE, and kinetic energy, we call it KE. So what's the goal? I want you to be able to explain the difference between GPE and KE and perform the appropriate calculations. So a couple more new equations in this unit. So gravitational potential energy, or GPE, is a common form of energy. This energy is a result of an object's vertical position. All right, and the equation is derived from Newton's second law. So I'll quickly show you where the equation comes from. So we know that we are calculating gravitational energy, EG. Okay, the other day we did, squeeze it in over here, work energy, which is force, times displacement. So gravitational energy is very, very similar to force times displacement. Okay. Our force, though, from Newton's second law was Fu ma. Now, if something is hanging, all right, so if I have a tree and an apple above the ground, force due to gravity is acting on that apple. So that's my Fg. So that means that Fu ma would become force due to gravity, mass, times g. So I can use that and plug it into that equation. So now my equation is mg, so it replaces the F, delta D, and instead of displacement, we're just going to say, well, how high is the object? So we're just going to change it to the letter H. So gravitational potential energy, Eg, is mgh. And there is our new formula. And it's just a form of our original formula, the work one we did yesterday. All right. So let's quickly try it out. So find the gravitational potential energy of a 20 kilogram hanging pot located 5 meters above the ground. So if you're walking uptown and you see pots hanging off the street lights, how much energy do they have? Well, Eg equals mgh. Mass is 20. 9.81 for our gravity. Height is 5. Now we just plug it into a calculator. And I get 981 joules. So therefore it has 981 joules of GPE. All right. If a 5 kilogram ball falls from 15 to 5 meters, how much GPE was lost? So here's our ball at point A. Here's our ball at point B. This height was 15 meters. This height was 5 meters. There's our ground. So how much GPE was lost? Well, we know Eg equals mgh. Now, what we need to do is we want to know how much is lost. So we want to figure out the lost energy moving from point A to point B. So the formula then becomes mg delta H. I'll explain why off to the side here. So if we do Eg for 15 meters, mgh, then we would get 5 kilogram ball, 9.81 times 15 meters. So we'd punch that through the calculator. 5 times 9.81 times 15. So this is how much energy it had originally. So 735.75 joules. Now if we find out how much does it have left, all right, mgh, so 9.81 times 5 meters. So 5 times 9.81 times 5, it's got 245.25 joules. So then we would find the difference. So what is the difference in energy? 735 minus the 245. What does that give us? 735.75 gives us 490.5 joules. So that is, I guess I could call this method 1. All right, so the long way, method 1. All right, but what's the only difference here? If we take a look at our equation, so mgh, so if we look, mass is 5, gravity is 9.81, mass is 5, gravity is 9.81. The only difference is our heights. So that's the only thing that's really changed for us. So back over to the other side, delta Eg equals mg delta h. We'll put a bar or a square around this one. So now you have two formulas. All right, the one from above. This is the change in energy. So that's equal to, oops, put the numbers in now, equals 5 times 9.81 times 15 take away 5. That's what that delta H means. So you gotta be careful when you're doing the subtraction, but that's 10. Okay, you can do that in your head. Times 10, and we get 490.5 joules. So it's the exact same answer as what we got with the long way, but it's a lot shorter. So that formula there is the change in GPE. Okay, so if we're talking about an object having a change in GPE, that would be the formula that you'd end up using. Second example, roller coaster. So I have the roller coaster shown. What is the GPE at point A? So if you can't really see it in the diagram, it's up here. All right. So what's the GPE at point A? Straightforward question. They just want you to calculate MGH. Now, it doesn't give me the mass of the roller coaster, and that often happens in questions in the textbook, and that's why I'm doing it here. You just leave it as M. Okay. So M, excuse me, times 9.81. Now, what's the height? We see that this is the ground, so this is the height above the ground, so it'd be 25 meters. So a lot of people get freaked out because there's no value for m. You don't worry about it. We just add it on at the end, times 25. So the answer is going to be 245.25 m, because we still have to multiply by a mass, joules. All right, so there is your answer for A, MGH. B part. What is the change? And there's that key word. What is the change in GPE? That means we're going to use the delta Eg formula, which is mg delta H. Again, we don't know the mass. Gravity is 9.81. Change in height. Well, the roller coaster went from up here down to point B. If you can't see point B, sorry, it's right there. So it changed 15 meters. That's the change in height. So 15. Calculating that out, we get 147.15 m joules. So therefore, it lost, all right, 147.15 m joules of energy. All right, so that gravitational potential, if the closer you get to the ground, the more energy you're losing through it. And C, what's the GPE at point B? Straight calculation of MGH. So again, we don't know mass. 9.81 times 10. So 98.1 m joules of energy. All right. So there's your calculation. There's an example where we have the word change thrown into a question. So it means you'd have to use your corresponding change formula or delta formula. Now the second part of this lesson is kinetic energy. Excuse me. So kinetic energy, all right, is the energy contained in a moving object. So if an object is moving, it has a certain level of energy. So the equation we can get from that comes from work. So our work formula, so I'm going back to EW again, and force times displacement. So we want to move to EK. And we're going to use our kinematics equations. So what I'm going to do, I'll just go through this quickly. You're not going to have to regurgitate this. I just want to show you where it comes from quickly. Again, force comes from Newton's second law, Fu ma. So I need to get rid of that acceleration, and we do that from our kinematics equation, v2 squared equals v1 squared plus 2a delta d. And what we do is we assume, for this formula, we assume v1 was equal to 0 initially. So we're talking about an object that started from rest and then began to move, which means that that part of the equation would disappear. I want to get acceleration by itself, so I'm going to divide both sides by 2 delta d. Again, you're not going to have to regurgitate this for me. 2 and delta d cancel out. So we get, therefore, acceleration is equal to v2 squared over 2 delta d, which we take and plug into Newton's second law. And kinetic force, I guess you could call it, is m times v2 squared over 2 delta d. All right, so I just plugged in, I replaced a, and that's all I did there. Then we take this and substitute in our force, so it becomes m v2 squared over 2 delta d times delta d. Okay, and that comes from above, right here, comes down. Delta d's would cancel, and your final formula is what's left. And I'm just going to give you the final format. So that divide by 2, I'm going to make it a 1/2 mv squared. All right, so there's your final formula, just like that. So how does kinetic energy work? So how much Ke, so I'm looking at the example now, how much kinetic energy does a 1 kilogram ball have traveling at 10 meters per second? So 1 kilogram ball, roughly the size of a softball, 10 meters per second, that's about 36 kilometers an hour. Okay, so not a very hard pitch. 1/2 mv squared, 1/2 mass was 1, velocity is 10 squared. So 10 squared is 100, and half of that is 50 joules. So a 1 kilogram ball, so a softball traveling at about 36 kilometers an hour, will have 50 joules of energy. All right. Now for the big curlers in the crowd, if a curler uses the same amount of energy on an adult stone and a children's stone, what would the difference be in velocity? So kinetic energy, we'll call it 1, equals 1/2 mv squared. So we know that the kinetic energy of the first stone is going to be 1/2 20 for the adult stone, and v squared. Okay, and be v1 squared. Simplifying that, ek1 equals 10 v1 squared. So we don't know what that initial value was. So we got to look at the other stone now. So our second stone, m2 v2 squared, ek2 equals 1/2. We know that the children's stone's 10, new velocity. So that simplifies to go to 5 v2 squared. So to finish this up, we know they're going to use the same energy. All right, it's given in the question. Same amount of energy. All right, so we know the two energies are the same. So that means that 10 v1 squared is equal to 5 v2 squared. I'm going to divide both sides by 5. And I get 2 v1 squared equals v2 squared. Take the square root of everything. So root 2 v1 equals v2. So that means that the second stone will be traveling at a different velocity. I'll finish this in the next example up in the next video.